So welcome everyone to the Friday Department of Earth Sciences, I guess TGIF seminar. Eric Attias is our speaker today. He got his bachelor's in Sea and Marine Environmental Sciences at Rupin Academic Institute in the town of Hadera, Israel. His master's and PhD were at the University of Southampton in marine geology and geophysics and marine electromagnetic geophysics. He came here to HIGP in 2019 as a postdoctoral fellow funded by the Ike Wai project, and now is a research affiliate within HIGP. Eric's research is really in cutting edge and an exciting growing field in electromagnetic methods in geophysics. We're starting to see a lot of really exciting results with that method and new developments of the method. He uses controlled source EM, either towed or ocean bottom receivers to image fluid flow or resistivity structure in gas hydrate provinces, massive sulfide deposits. He also combines that with seismic imagery. His other research is involved MT methods for looking at larger scale or deep structure, such as the lithosphere-asthenosphere boundary. And he's here to talk about some very recent work using marine electrical imaging to image the hydrologic system offshore Hawaii here. So go ahead and take it away, Eric.
Thank you, Garrett. Thank you for this introduction. And thank you everyone for joining us this afternoon for my talk. What I'm going to present to you today is marine electrical imaging experiment that I conducted at late September 2018 with the aim to detect and quantify image submarine freshwater reservoir offshore of the west side of the Big Island. This work is mainly in collaboration with Scripps Electromagnetic Laboratory, which provided the instruments to do that. And here you can see a bunch of photos from the survey. We had fun. It was very hectic, but we kind of enjoyed every minute of it. So you'll see more of it later on. So to change slide. So I'd like to start with some industry article that I recently stumbled upon, where they state that the World Health Organization basically predicting that in the next 10 years, there's going to be 2 million people that will not have access to clean fresh water. And therefore, the article continues and said that the Department of Energy basically are deploying a suite of programs to kind of finance different kind of research that will address this issue. And some of it will be kind of supporting offshore freshwater research. Now, one of the first papers that brought to light the notion that there is a lot of freshwater offshore that is in form of fresh or brackish groundwater reserve is a Nature review by Post et al. And he basically, you can see in that map how he illustrated all the locations that offshore groundwater were detected mostly from drilling studies. What I want you to notice that there is no information about the Hawaiian Islands so far. Post et al. Continues and he says that, okay, those new renewable reserves of freshwater kind of make the case to promote this future research. And you can see here some of the properties of the spatial extent of the freshwater reserve that he highlights in his paper. If you look at the New Jersey one, a recent electromagnetic studies conducted by my colleague, Gustafsson et al. In 2019, basically confirmed the drilling studies that there is a freshwater layer reservoir that extends 90 kilometers offshore New Jersey, and it's about 200 meters thick. So that shows you that the electromagnetic towed system can give you reasonable results similar to drilling studies. They used an earlier version of the system that I used in this study. So my study is part of the larger project called the Ike Wai project. It's a 5-year project that aims to understand the aquifer system in two Hawaiian islands, in the Big Island and Oahu. And as you can see, this is a multidisciplinary study that includes geochemistry, microbiology, land geophysics, some modeling. And I'm just gonna focus on the marine geophysics part, which what I dealt with, and only on the west side of the Big Island. I would like to start with this rainfall map of the island of Hawaii. You can see the Hilo side has a lot of rain. This is from June 2019. And the Kona side, the west side, is relatively dry. And this is where obviously most of the population and tourists exist. Therefore, we kind of focused our study throughout this entire system, offshore parallel to the west side, that extends about 50 kilometers through that area and up to about 4.5 kilometers from the shoreline. And you'll see more specific maps later on. Now, the Ike Wai land study, our land region, is basically focused on the Walalai terrestrial groundwater system. Now, previous studies, or recent studies, I would say, kind of predict that there is a discrepancy of about 40% between recharge of freshwater at high elevation and discharge at the coastline. So that's a substantial amount of water that's getting lost somewhere. So where all this water go? It could be kind of propagating parallel to the coastline, and or it's coming out on the as springs as the shoreline. So the U.S. traditional hydrological model basically suggests that complex dike system, faults, and lava tube basically transport the fresh water from the land to the coastline as basal lands, where fresh and brackish water are released just by the coastline as a submarine groundwater discharge. And beneath there is some brackish layer, and then there is nothing under, it's just seawater. So I wanted to study if that is indeed the case, and if we have maybe deep submarine freshwater reservoirs that extends to the offshore. Now, as a marine geophysicist that mostly specializes in electromagnetic methods, obviously I wanted to do marine control source electromagnetic study. Now, normally when we do these experiments, we use deep towed system that requires a large vessel and a bunch of instruments, as you can see here on the deck. And this is just a photo from a research experiment we did in Alaska. So this is really high, expensive, large scale kind of setup. And you can see that those are some of the instruments that we use. We have a transmitter, CSM transmitter source. Basically, in the academic world, there is only two institutions that has that. It's the Scripps and the one in Southampton. And we have some seafloor receivers and towed deep receivers. And basically, we go with the vessel, we transmit high voltage converted to high current. The current emits on a dipole, electromagnetic dipole, projected down to the subsurface, and the returning signals are recorded by seafloor receivers and by a towed receiver. Now, ideally, to study the Hawaiian system, the freshwater system, I would like to use a deep towed system. It's called the Vulcan system that was developed at Scripps. But the problem with that it's, well, why to use that? It's because it will give us high resolution of the shallow structure because it's high data density, and we towed the source about 50 meters above the seafloor, and therefore we get a nice penetration to a depth which is about half of the length of the source receiver offset. In this case, they use it for gas hydrate. We could do it for the fresh water. But there's two problems, unfortunately, why I didn't use this system, because A, it requires a large vessel and a deep towed system that is substantially expensive. And second, to drag this entire array of about 1.2 kilometers in the sharp bathymetry of the big island would have made it very challenging not to crash that array into the slope at some point. So it's more suitable to more moderate seafloor structures. Therefore, instead, I use the same kind of system, which has the same electronics, but it's a surface towed system that we call porpoise system that was recently developed by the Scripps electromagnetic laboratory. And in this system, what do? We can carry it in a small vessel, transmit some current into a dipole of 40-meter length, about 100 amps. By that, we generate an EM field that goes down to the subsurface, interact, and wherever we have something resistive, in our case, groundwater, the secondary field will be recorded by 4 of those receivers on the seafloor, and the changes of the resistivity of the subsurface will be translated in terms of the amplitude and phase that we record. So the amplitudes will not decay as much, and the phase will be faster. And this is something that later we can translate with an inversion to a resistivity model of the subsurface. The advantages of this system that it's relatively much cheaper than the deep towed system. We can use a small survey boat. We can deploy and recover the system pretty fast. It's sensitive to resistive structure, and it gives us depth penetration to about 500 meters. The disadvantage is that we can only use it to a depth of water of about 100 meters, because otherwise we don't have enough source receiver to get penetration, and also the current that we have to emit will not basically, will reach the seafloor, it will decay within the conductive water column. So this is what we use in this study. And here you can see just an example of how easy it is to deploy that system. We can do it manually from a small boat, and the deployment and recovery of the entire array took us about an hour, which in large vessel, it's about 3 hours to deploy a system. Besides this electromagnetic system, we also acquired another 4 additional supporting data set. We took a marine magnetometer because of the magnetic structure to see if we can detect some intrusions. Seafloor multi-beam high resolution system with backscatter, and also we recorded the water column multi-beam signature. So this is how the system all looked when we towed it behind. So it's crowded, and actually the captains say, yeah, no, it will never gonna work. It's gonna be a mishmash, but I believed it will work from my experience. And as you can see here, what we had on the port, on the starboard side, the magnetometer, about 70-meter cable. It was about 6 meters deep. The porpoise array extended to 1 kilometer, and it's on the surface. And the antenna, short and long antenna that produced the electromagnetic field, was in the port side. So it actually worked beautifully. The only problem that we encountered is you don't see it, but at the end of the array, there was a chase boat. And there is an extensive fisherman kind of traffic, boats offshore of Kona. So the chase boat really worked hard all the time to keep our array clear from boat, to cut basically in the middle of the array, and then cut our entire kind of system. So that was one of the most challenging things that we had in this survey. So this is another kind of disadvantage of towing things on the surface. So if we look at the survey parameter and the map of the survey, basically that survey included or covers the entire area parallel to the Walalai terrestrial groundwater system, from Kiholo Bay all the way south to Kailua Kona, which is about 50 kilometers of coastline. And As mentioned before, we acquired 5 different data sets with about parallel survey of land of 8 with increasing seafloor depth from 10 meter to about 70 meter of water depth. And we had a few perpendicular kind of cross lines too. So overall, the depth or the extent of where we could survey was governed by keeping the water depth below 100 meters. So that gave us about an offshore range from 150 meters close to the coastline to about 4.5 kilometers far away, where the seafloor is shallower at the north area of that system. So in total, we got 220 kilometers of data, of CSEM data, and we concluded that in 8 days of work, pretty much 12 hours of work every day. This is an example of the multi-beam system, the high-resolution multi-beam system that we use. And the main purpose of the multi-beam system was to highly, and I would say, to accurately represent the fluctuation of the seafloor, because this is crucial in CSEM modeling to know the topography of the seafloor, because it changes the signal and what you will get as a resistivity model at the end. So that was the main kind of reason to use a high resolution multi-beam system, but it also showed us how the bathymetry is highly fluctuated with the basaltic slope, and we have very low sediment content, which is mostly a basaltic area in this region. The magnetic data, we have some preliminary 3D inversion model of the magnetic data, and you can see here that there is some structures of magnetic intrusions, multiple all around the area of the survey, that they might be the kind of governing or structure that controls the flow of the fresh water while they're reaching the offshore. But this is really preliminary work with the magnetic data, and it's still in progress, so there is no significant conclusion to be drawn from that and to link it to the freshwater flow at the moment. I just wanted to show you that there is an interesting magnetic structure of intrusions in that area that we surveyed. So coming to the main data set of this study, which is the CSEM data. But before I show you the inversion model, I want to show you a bit of the raw data, kind of interesting things that we discovered in the raw data and the waveform spectrograms of this data. So here we use the doubly symmetric waveform, which is focusing its power in the higher harmonics, which here correspond to 3 Hertz, 7 Hertz, and 13 Hertz. And that is basically allows us to image the subsurface of the shallow structure in high resolution, as opposed to a square waveform that is mostly the power is situated in the fundamental frequency of 1 Hertz, and therefore you cannot really resolve much of the shallow structure in high resolution. And on the right side, you can see the spectrogram, or basically the power that we record while switching on and off the transmitter. So all the blue areas, it's just ambient noise of the seawater. There is no transmission. And the warm colors areas is where we switch the transmitter. On the left side is when we basically transmitted 70 amps. The right side, when we transmitted 100 amps. And you can see clearly that the 100 amps kind of resolve the band. You can see horizontal bands of those frequencies, 3, 7, 13, much better than the 70. So that was an experiment. Then we used for the entire server 100 amp. And you can also see that those bands are kind of decaying with increasing offset. So the purpose one, which is 250 meters from the source, is the highest. And then it gradually decreases until purpose 4 has a little signal, which is 1 kilometer away. But we still got valuable information from the data from purpose 4 also. So before I'm going to show you the raw data of the Hawaiian data set, something that is really interesting to see, just to compare the data set. This is the raw data of amplitude and phase from a deep towed receiver of the gas hydrid province offshore of Norway. So you can see clearly both in the phase and the amplitude that there is an anomaly, which in this case, it corresponds to vertical gas hydrate chimney. But more importantly is that you can see, and especially in the phase, that the background in this region is basically clay homogeneous sediment, which kind of tells you, okay, we have clay, 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 nothing is so interesting. It's sediment saturated with seawater, and when you have an anomaly, it spikes up both in the amplitude and phase. But now look at the information from Hawaii. So yeah, we detected some anomalies, both in the amplitude and phase, but look, and particularly also the phase, because it's more sensitive to changes of the subsurface, you can see how the background is very fluctuated and changing. And once I saw that, which is really uncommon to see, I realized that we have a very interesting and complex data set that is heterogeneous, that probably will have a complex structure later on. So we take that raw data, we stack it, we merge it with the navigational information, and the next step is to invert it. So we apply the CSEM to the inversion using Mare 2DEM, which is basically a finite element algorithm, non-linear regularized, that is conceptually based on the Occam inversion. Now, the beauty of the Occam inversion in Mare 2D is that there is the Lagrange multiplier that automatically try to find the smoothest model to a predefined RMS misfit target that you assign to the inversion. And we normally keep it at 1, ideally to fit the data and that is done basically automatically through the Lagrange. This is the example of how I basically constructed the mesh of my starting model. So this is a half space starting model. So we define the air space as a fixed parameter. The water column here is and the subsea floor is as free parameter, which means the inversion can seek the specific resistivity that the data requires. Now, this is an interesting case because normally in CSEM, when we do a deep towed CSEM, we also define the water column as a kind of few layers of fixed parameters based on the conductivity structure that we acquire from CTD during the cruise. By that, we kind of substantially reduce the computational cost because there is no need to invert the water column because we're interested in seafloor. And if we have a nice information which doesn't change too much about the conductivity of the water column, most of the people who invert CSEM data use the water as a fixed parameter. But I realized that this is a key feature that in this particular data set, I had to define the water column as 3 parameters, and I will basically discuss that further later on. And this is basically the most important slide of this entire presentation. What you can see here is 22 inversion models that covers the entire region of the study. And those are isotropic models, but some of you may say, oh, you should have inverted in anisotropic also, and I did so. The anisotropic models also show a similar structure, which means the isotropic models can resolve the structures, the electrical structure in this region just as well. And what I want you to see that we have a kind of very consistent formation. So at the top where you have red colors, it's basically basalt saturated with seawater. Beneath that, you see the blue shades colors. It's basalt saturated with freshet, which is brackish, to freshwater. And then there is another layer of basalt, the red color, that is saturated with seawater. And then beneath it, another layer of freshened water. And you can see how well all the lines tied up together, and also the cross line and 2 agrees with their parallel lines. Another feature is that we found from around Kailua Kuna that we have this large basically four parallel survey lines show that from 300 meters, there is a large resistor, which we interpret as a large-scale freshwater reservoir because its resistivity is about 1,000 ohm. And we tried to do some volumetric estimation using arches an equation of state, and we kind of concluded that this entire area basically have a volume of about 4.7 cubic meters, while assuming a porosity, which is typical porosity, of 20%. Now, if you look, you can see on this left corner what is written line 3 north. To see that two-layer pattern, we'll zoom in into line 3 north, and then you can see how we have conductive layer, which in the top, it has some sediments, plus the basalt, and then a resistive layer, and between them, there is a low permeability layer, which is most probably ash and soil that accumulated in armor this structure of the lava flow before it's submerged to the marine environment. And that acts as a confining unit. So we have a resistor layer between it. Then we have another conductive layer, which is basalt and saturated with seawater. Another low permeability layers that keeps the water from flowing upward. And then another resistive layer that extend to about 500 meters. Now I want to note that this multi-layer structure can continue further down with more layers, and further out from the coastline. You can see the line on the map from the right where we image that. But due to the limitations of our system, I couldn't see any deeper or further. So this is kind of an example, but it might be that those layers are continuing to the deeper structure. This is another example of a different line, a bit southern from the first one, close to Kailua Kona, and you can see the same kind of structure. We have conductive, resistive, freshwater, and then another conductive, another freshwater layer. It's more fluctuated, probably due to the nature of the lava flows in this region. And you can see on the table some of the parameters of the inversions, and that is kind of representative to all of the inversion that we had. And we basically fitted most of the inversion, or all of them, to about one RMS misfit of 1. And you can see the fits from the data to the model. You can see nice fits both in amplitude and phase with randomly distributed and low values of normalized residuals. So that kind of give you confidence that this is kind of a good inversion model that you can trust the results of it. So coming back to show you that entire multi-layer system of that region that we discovered. Based on that, we constructed a new conceptual model of how freshwater are transported offshore the big island on the west side. So this is our new conceptual model that basically shows that rainfall water percolates and recharge the aquifer, the land aquifer system. And then they start to flow downslope when they meet the low permeability layer of ash and soil. So if the water table is above, those permeability layers act as perching formation. If the water table is below, they basically confine those water to flow with the porous basalt all the way through to possibly the shelf edge, depending on the hydrostatic head levels, all the way to the slope of the formation. And if there is no structural barrier, they will probably keep on going until they will release as springs, as SGD, but in different layers and different depths. So that's our new conceptual model. And this is basically kind of a paradigm shift from those current traditional conceptual models that all shows the same kind of every paper that you open on a Hawaii groundwater system. You have the basal lands that are basically coming out. If you look at the Bishop et al. 2017, that the basal lands bring fresh water to the coastline, releases SGD. There is some transition zone with brackish water, but beneath it, it's all salt water. It's all ocean water. There is nothing to more freshwater layers beneath that seawater layer. And this is, you can see an image that I took, an image that I downloaded from the Board of Water Supply website, which this is basically the model that they're currently using to calculate their aquifer storage and sustainable yields. And by doing so, they neglect those multi-layer formation of freshwater that are beneath the ocean. So it might be useful for them to use that. Now, our conceptual model, you can say, okay, it's only electromagnetic imaging. So what? But we have some supporting evidence for that. So worked by Don Thomas from '96, you can see that 2 drill sites at the east of Hawaii also show the same formation, that you have some seawater beneath the basal land, seawater basalt, some thin freshwater layer, then another layer of seawater, and then another under confining layer, 150-meter thick of freshwater layer. So it shows you the same kind of layering pattern, and this is on the east side. So you might say we're in the west, could be different. But I will show in the next slide that it's pretty much the same. But the more interesting thing is that when I kind of looked if there is those multi-layer formation in other islands, I discovered those 5 islands, Galapagos, Comoros, Reunion, Cape Verde, and Hawaii. Those islands show exactly the same multi-layer formation, some of them with 2 and 3 and 4 layers from onshore studies, electrical studies and drilling studies. So in a paper that we just got accepted in Science Advances, we propose that this formation, the conceptual model that we show, it's probably the governing mechanism in volcanic islands of how water are transported from the land to the offshore environment. So you might say, okay, this is the east side, might be different on the west side. But look at this slide. You can see that we have information from a Kamakana borehole, which is situated about 3 kilometers diagonally to line to south of our study. And you can see that from about 30, the salinity profile of it, from about 350 meters, the salinity substantially dropped to freshwater levels. So just to remind you where line to south is, you can see it's on the right corner of this image, which is basically in front of Kailua Conad, where we saw this large-scale freshwater reservoir. And if we zoom into this line to south, look where the transition from fresh to freshwater is, around 300 meters. And it's really close to that borehole. So this is kind of give us confidence that what we see in our modeling consists with the borehole data, which kind of confirms that we probably seeing the right structure, electrical resistivity structure of the entire region. Another interesting fact about this line, it's something that I noticed during the cruise. While we're acquiring data along this line, I noticed on the cliff just in front of us a lot of lava tubes in the formation on the cliff. So I kind of postulate that those lava tubes kind of layer can maybe kind of propagated downward, and you have more lava tube, and that's what gave rise to the high volume of fresh water, because they act as like conduits with 100% porosity of fresh water that travels and goes all the way to the area where we found that large scale freshwater reservoir. So what I show you until now was the subsurface imaging, electrical imaging of that entire region. Another thing that we discovered accidentally, and that was something very exciting, is that the system we use can actually detect freshwater plumes within the water column using electromagnetic data inversion. So why did I even try that? Before every day of survey, and then the end of every day of survey, we did the CTD cast to the depth that extends to the depth that we wanted to serve in that day. And as you can see here, with every CTD measurement, we always had an anomalous region where the salinity drops and then the resistivity increase, which is a clear signal to freshwater kind of layer in that area. Here you can see it between about 2.5 meters to 5 meters, but it was appearing in different depth in every day of the survey. That kind of sparked something in my mind, that I realized that the water is the conductivity of the water here in this region is so fluctuated that I must invert the water column as well. Otherwise, that the mistakes in the water column resistivity can propagate downward to the subsurface, and I will get wrong inversion models also of the subsurface. So back to the slide that you already seen, and not only that I converted it, I discretized it as three parameters. You can see that I give it a much finer mesh. Yeah, I got like each finite element of 10 meter over 20 meter, while the subsurface is 10 meter to 1,000 meter. And why is that? A, because those transition of sharp salinity changes are kind of small scale. And B, because the water column is closer to the array of the receivers. And therefore, the receivers is much more sensitive to changes in the resistivity as close as the data is to the receiver. So any mistake within representing the resistivity structure beneath the seafloor, the water column that close to the receivers, can really propagate an error that will translate it later on to the seafloor, to the subsea floor. In the beginning, I was trying to invert the data with the water column as fixed parameter, and I got horrible models. And once I did that, everything switched on, and I started to get like reasonable models. And not only that, you can see here that by inverting the water column data, you can see two lines, line 3B and line 3C. I can see a clear pattern of vertical flow from the subsurface layer into the water column, crossing the subsea floor, and give rise to a freshwater plume. Not only that, we can also image like disconnected from the freshwater plume, really strong resistor as the surface, which we interpret as surface freshwater, that probably basically fluxed from nearby location of plume and drifted into our survey line. And you can see it's well described in those two images. So we tried to give some volumetric estimation of those plume. And thanks to Henrietta and Christopher Scholler that helped me with that. We basically took that information of the plume, of the resistivity, transfer it to conductivity, and then to salinity through equations of the salinity scale of 1978. And then you can see in the lower image, we can get a nice representation of the plume in terms of salinity. From that, we can basically derive the plume unit volume, its average salinity, and the fresh water content of it. We got about 85% of fresh water in that plume. We did the same, this is line 3A, a section of line 3A. We did the same to line 3D, which here you can see a much more robust plume, wider plume, much more resistive at the top, probably getting some influx from a nearby plume. And by doing the same procedure, the same calculations, we got that the freshwater content here is about 87%, which means there is a substantial amount of fresh water that fluxing in this region to the water column. That the information, I think, could be very useful to hydrogeological modeling and also to oceanographer and to understand the biochemical cycles offshore this region of Hawaii. This is a bit of anecdote that I wanted to share with you. Well, it appears that there is a worldwide interest in freshwater, offshore freshwater kind of studies, because we ran a blog in the website of this project, and it seems that we have a lot of views. We have about 5,000 views at the moment from 55 countries, this has kind of made me happy to know that this information that not only stays within the community or the Ike Wai project people, but it also propagates outside of Hawaii, that people can understand that, yeah, this is the first time that electromagnetic imaging in a volcanic setup can resolve freshwater reservoir, and to kind of bring up the awareness to offshore freshwater that could be a potential resource in the future. And I would like to end with with a short time-lapse video of the porpoise array recovery. That's the last one we had in the end of the cruise, which is basically 1 hour of work to recover that entire system, which is compressed to 2 minutes. So hope you enjoy it.
Coming down to the light of day, we got many moons that are deep at play. So I keep an eye on the shadow smile to see what it has to say. And you and I both know everything must go away. What do you say? Spinning around letters on my heart, it's like a little light in a touching dark. You got sneak attack from the zodiac, and I see a bright star. So please and go by flow and go away. What do you say? Yeah, you don't know my mind, you don't know my kind. Talking this is all part of my design. Good job, everyone. Successfully.
Yeah, that's pretty much it. And for those of you wondering where was I in this video, I was running the winch, so I wasn't stacking. I would like to thank all my collaborators, both from Don Thomas, Henrietta and Christopher, and people from Script, Steve and Dallas, and all the people in the acknowledgement that were kind enough to share their information about Hawaii and Hawaii geology to help me understand what the data means, and that made this project successful. So this is pretty much what I have for you today. Thank you, and I'll welcome any questions you might have.
All right, great. Thanks a lot, Eric. Yeah, so if you'd like to, if you have questions, feel free to, you could type it in the chat, or you could actually, let's see if I can, I'm not sure if I can see everyone, but you can go ahead and unmute your mic and just ask a question.
Hi, Eric. It's Hannah. I was just wondering, so geology is static, it doesn't change, but you're applying this survey to geology filled with different fluids, two different, salty and fresh. How does that change your approach? Does it change, for example, could tidal influences or big rain, seasonal changes, could they change what the lenses look like? Like, would you expect the same survey if you came back at another time?
Yeah, so one of the advantage of this study site, because of we have all this submarine groundwater discharge, as opposed to all the location described by Postedal, he described places that are non-renewable. Now we're proposing that this is a renewable system because it's always releasing water to the water column, fresh water to the ocean. But still, what I did, it's a snapshot of the situation at the moment. So realistically, or ideally, if I will do the survey exactly the same, because it's really hard to do a time-lapse CSCM because all the parameters has to be exact. so it's almost invisible. But if I would do the same after a big rain or after a period of more rains or a period of dry, yeah, that image will change for sure. But if my conclusion is that if I see something that is so consistent the entire region to about 50 kilometers, that you always see those two layering formation, so it means that there is always some accumulation of basic levels of water over there. And obviously it varies depending on the fluxes of submarine groundwater, but it's kind of one snapshot that represent the area to the time that the data was being acquired.
And does the time that it takes to do the survey, are there any tidal influences? I'm not sure how long it takes you to do one line, but is that seen in the data or not at all? They're too small.
No, because the data doesn't care about tidal information. Basically, you project an electromagnetic waves, and it could decay or not, depending on the water layer. Okay, but what the data sees in the subsurface, this is what you basically see in the changes in phase and amplitude, and therefore you translate it to the inversion model. So it wouldn't affect the bulk resistivity of those features because it's how thick the layers are multiplied by their resistivity.
Oh, thank you.
So I think, so the question maybe it had to do with, did the tides change the structure? Is that, is there a possibility of the tides changing the structure that you're imaging?
No, you mean like a normal daily tide? No, it won't change the structures. It might change the fluxes of the freshwater plume, maybe more hydrostatic pressure on those plumes. But the deeper structure, the first structure of freshwater that I see is about 130 meters beneath the surface. So I don't think there is any tide. I think they're intrinsically linked to the formation from the land that transport those water to the offshore environment.
Daniel Douglas has his hand raised in the participants. You want to go ahead, Daniel?
Yeah, sure. That was very interesting. Thanks, Eric. I just was wondering if you could run through again the idea behind the conceptual model and like how these like distinct layers form that like separate the fresh water subsurface layers. Because I don't know if I missed that, but I would just
Yeah.
like
So here, if you can see that slide now that I'm showing.
I cannot at the moment. No.
Okay. So it doesn't share the screen. Okay, maybe now.
Oh, yeah, that's good.
Okay, so basically what we're suggesting is where the fresh water percolates into the land aquifer, depending on the water table levels, it hits at some point a low permeability layer of ashen soil that was formed in between eruptions. So if the water table is below this low permeability layer, the water, it acts as a confining layer from above, so the water must flow beneath it and cannot escape upward. If the water layer is above, it's kind of perching it to the upper formation. Therefore, between eruptions, you have this kind of multi-layer of axial soil of low permeability layers, and that's what keeps the water flowing within the porous basalt. And this is what basically Don Thomas saw in the other side of the island, while he drilled through those layers. So there is always some confining layer that is above the freshwater layer, and that basically what keeps the water in that structure and guided through the slope to the offshore. If that makes sense.
Yeah, thank you.
Taylor, you have your hand raised in the.
Hey, Eric, it's Brian Taylor.
Well, actually, Brian Taylor can go first, and then Taylor Vitti after Brian Taylor. Go ahead, Brian.
Oh, sorry. I didn't hear you use the word coral once in your talk.
Yeah, that's true.
But we know that off Hawai, along the rift zone, I mean, we've dove and sampled. We know there's terraces of coral in the area where you did your survey. How might they be expressed in your CSCM data?
Well, the terrace, I know there is a terrace, and obviously that is mentioned in the paper from your work. But the thing is that we look at the bulk resistivity of the imaging. So looking at the subsea floor or from the multi-beam data, if the coral terrace are compressed enough to show kind of a bathymetry structure, so they are confined or considered within the modeling as the seafloor. If they're not, if they're too porous and the multi-beam basically image the subsurface, the seafloor topography differently, then I wouldn't see them. So it doesn't really matter to me if it's terrace or if it's basalt, as long as I know what is the formation of the seafloor, then I know how the modeling, know how to basically account for those changes in topography. If that makes sense. If they're very porous, if they're very wide, then they will be translated as a water column, if that makes sense.
But like in your other margins, I mean, they're a particular kind of sediment, if you will.
Mm-hmm.
There are organic rock sediment. If they're tens of meters thick, they're different than water and they're different than basalt. So
yeah, so if it's basalt in the shallow structure, probably have some sediment and some weathered ash. And that's what gives rise to the conductive region at the seafloor, near the seafloor. So the thing is with electromagnetic, it doesn't tell you what it is. It tells you what is the electrical structures of it. What it is your interpretation based on the knowledge. But we can make some assumptions that everything that is conductive in that area, it could be some basalt with intrusions of seawater, or it could be a sediment. In that case, if it's really thick sediment, it will kind of eat the electromagnetic signal, and then we will be able to image to a shallower depth. But the discrepancy between coral and the actual basalt, you cannot really account for that with the electromagnetic imaging.
Thank you.
Welcome.
Taylor Beatty had his hand up.
Hello? I don't know if you can hear me. So I'm curious. I know that you didn't do like a full like a 2D receiver grid, but I'm curious if it would be possible to invert this data set in 3D with like MARI 3D EM instead of just like stitching together 22 line inversions, and whether or not there would be any value to that if it's possible.
Yeah, well, let me take you to the slide of the map. Yeah, if you can see this slide.
Yeah, it's loading a little. Yeah, there we go. There we go.
Yeah, so the only places that you can actually do a 3D modeling will be south of Kailua Kuna. You see we have like 3 lines that are pretty close to each other, that are correlated, they're basically parallel to each other. So that might give us a 3D grid, and the structure in the north, in the line 3 north and the following. And I actually spoke about it with Kerry Key, and I will try that once MARI 2 3D EM will be ready. What we can get better volumetric estimation to see it as a block. Then I can calculate better what's the saturation of the freshwater in those layers. But since you've done it independently as 2D lines, and all of them are consistent with each other, that gives you a great confidence that that structure is continuous. So it wouldn't change the story. It will only change our ability to quantify those freshwater reservoirs, basically. But yeah, it's something that I plan to do in the future.
Mm-hmm. Cool, thank you.
Welcome, Taylor.
Yeah, if I may, so I had a similar question. So it looked like the question had to do with how important might off-plane structure be. but it looks like from the images that you showed that you don't have a real strong evidence for lots of variation perpendicular to your lines. Is that overall, you're pretty confident that what you're imaging is not
Yeah.
in any way artificial, given potential cross-track variability?
Yeah, look at crossline 1 in this image and crossline 2, and look how well they're correlated, where the freshen layer, the second freshen layer comes in to the picture. And
Yeah.
once you have, obviously I collected the data continuously, but due to the 2D modeling assumptions, I had to kind of chop the data to create something that will fit the model into 2D. But once you have so many lines in such a large scale and there's consistency between them, it's really hard to argue that the structure is different or we're missing something over here that is not represented with those lines, I would say.
I hate to interject too, but I'm wondering, now that you're talking about this, Garrett, it feels like you would see that signature when you did the anisotropic inversion too, with some kind of off-axis influence on the line. And if the anisotropic one looks similar, then that kind of feels like it might be further evidence that you're not getting that kind of effect.
Yeah, the anisotropic models show the same pattern, but less robust, because with anisotropic inversion, you give more freedom to the model. And therefore, you get a smoother model that fits the data, and therefore the features as not as strong. But it's basically showing the same structure, which makes sense because anisotropic signature mostly rise when you have different sediment layers in different orientation. But here the sediment content is very low, so there shouldn't be much anisotropic influence.
Mm-hmm. There's a question in the chat from Gregor Visa. He's wondering if the structure, I assume the resistivity structure you're seeing in the water column, can allow you to place estimates of flux of fresh water or flux of mixing.
Yeah, that's something that we ponder upon, me and Henrietta and Chris Schuler, when we were doing that. But it seems that the uncertainties are wide in terms of resident time, and since it's a one snapshot, if we had a time lapse, we might have been able to do that. But it seems that doing that will be introducing too many assumptions that kind of deviate from the realistically kind of fluxes of that region. So we decided not to do that at that stage.
My question was a little bit different. I remember in the past reading papers where reflection seismologists, when they shoot their lines, they have to make water column velocity corrections. And through doing that work, they recognize different water masses. So they took their solid earth tool and turned it into a water tool. And so I'm asking a seismic velocity question. I know there's big temperature contrasts in the water that's leaking out.
Mm-hmm.
So I'm wondering, if you were to do seismic, could you get good aerial coverage of the water pretty quickly and then try to quantify flux that way? Because you have a kind of snapshot of all this fresh water that's unstable rising through the water column, presumably.
Well, I don't know if, I don't know where you've seen that, but seismic has to have some, I think some, how do you say, some reflectors. And I don't know if that kind of the changes in temperature give them such a reflectivity changes in reflectivity to kind of
if it's too continuous
that.
to pick up. I see what you mean. Yeah. Okay.
Yeah. So, and even so, it's the fluxes to calculate fluxes. It's kind of challenging from a one snapshot. Maybe Henrietta, you have something to add to that?
Well, I guess I would just really highlight the volumes that even the lowest, most conservative estimates are staggering. So the discharge with the assumed residence times that we got from the physical oceanographers, the discharge rates would be really significant, even from one plume. So that's why we were maybe trying to look into it more conservatively.
Okay, thanks for that. Sorry if it was a little bit weird.
No, it's fine.
It sounds really relevant to me, actually. Don Thomas, you have your hand up?
Yes, I just wanted to ask Eric, do you have a sense for how deep a water depth you might be able to use this sort of resistivity estimate the way you did here in the image that you're showing on the screen now, where you'd be able to track this offshore?
Yeah, well, using this system, it's kind of limited to about, I would say, 90 meters of water column. I didn't get any clear signal, coherent signal. It was mostly noise from the receivers, because we emit 100 amps that translated to electromagnetic field. But since the water column are so conductive, that basically ate the signal before it went to the subsurface and recorded back. So I would say realistically, yeah, you can see that image, it's about 60 meters of water. So I think, yeah, 60, 70, maybe 80, or we can do it with more amps. But that's a bit of a problem with the system. With the current system, it's hard to get it up more than 150 amps. So I would
Great, thank
say
you.
about 100 meters, ideally.
Roy Hardy, go ahead.
Oh, okay. Thank you. Can you hear me?
Yes.
Okay, thanks. Sometimes my microphone doesn't work. But anyway, thanks, Eric. Good presentation. Very pertinent to what we've been doing at the Water Commission over the years in Kona. A couple questions. First is, and maybe I missed it, but you mentioned the Kamakana deep monitor well, and you used the data from that, but I didn't hear about the Keopu deep monitor wells, which are south of that, Kamakana, and they, basically show similar freshwater. And I just wondering if you had seen that and incorporated it to correlate with the levels that you're finding. That's my first question.
Yeah, we have seen that basically, and Don Thomas can answer you more in particular to that, but it's kind of it's still confidential information. I don't know why, but we got the permission to use this well, but we're aware of that. Don, if you have something to add to that.
Sure. Yeah, Roy, we had talked about in the discussion when the paper was under review, we were asked if we had any land-based wells that had seen similar characteristics. And we incorporated both the evidence from the Keopu wells as well as the Kamakana well. And it turned out the Kamakana well, we had this very clear demonstration of the resistivity variation with depth and the resistive freshwater coming in at the bottom. And so that was presented in response to the reviewer question. Of course, I'm hoping to get a paper done myself that incorporates the Keopu, the Kamakana, as well as the work that we did up in the saddle, and the Hilo boreholes. We've seen this now in several locations where we have these confined aquifers that can easily explain why we see this freshwater offshore.
Okay, thanks. Good to hear. Just FYI as well, we are beginning to do another deep monitor well up in Koloko above the national park to see if we can find similar freshwater below the saltwater. It's at the Board of Water Supply. There, I can't remember, 610 tank, I think. So more info in the future, hopefully, to help with this.
Yes, definitely.
My second question is, where is that photo on your desktop, or that blue slide? It shows looks like bathymetry offshore on your desktop.
Which
I don't think it was part of the presentation. It was just what you had up at the end. Is that the Kona coast?
Yeah, yeah, I guess so. You mean the one that is now?
No, it was the earlier one that showed the layering down the slope.
Yeah, it was the last at the end of your presentation. It looked like it was your desktop, and it was blue, and it looked like offshore.
Okay, that's you mean the yeah this one. You mean this one?
Well,
No.
kind of looks like that. That's green. The other one is at the end, though. I think it's on your desktop, where everything was blue.
I'm not sure what you're referring to.
It might be your desktop.
Yeah, could be. Yeah,
That's the one.
It's just something for Apple backgrounds. I have no idea.
Oh, but you don't know where it is? Oh, okay. I was just wondering if that was offshore Kona, maybe.
No.
Okay.
It's kind of slight background.
Okay, thank you.
Welcome.
There's another question about how you might be able to look deeper. You mentioned possibility increasing the amperage of the source. What about changing the interval between the porpoises?
Yeah, so the study I showed you in the first slides by Gustafsson et al., which is basically Kerry Key's group, they used a 300-meter dipole, so they generated much stronger transmission, and their array length was slightly longer than ours. So they could reach a depth penetration to about 180 to 200 meter. That is one option, but that means you're throwing a big kind of system on the water, which is extremely, and we got like 2 fishermen boats that ran into the array, but luckily they didn't cut it. The ideally would be to use a deep towed system, but I kind of struggle with my mind how to use it in this topography without destroying it. It's almost impossible. So that would be ideal, because then we can fly, no matter what the water depth is, we can fly the source about 50 to 100 meter from the surface, from the seafloor, and then have a huge dipole, inject a lot of current, about 250 amps, and then we can image for a few kilometers with seafloor receivers. But yeah, a combination of longer array and higher amp of the emitted current, that will give you more penetration.
Okay. Another question. Is there any work to compare these data to fisheries data offshore Kona? Areas in particular of good productivity?
Well, interestingly, I didn't show it here, but we also intermittently collected the multi-beam for the water column. And I did saw an area where I detected a plume that there was in the water column some blob of possibly a skull of fish. But there is really very little literature that connects between fish and freshwater column or freshwater fluxes, the interaction between them. I just spotted it just by looking at the water column data, but it's very kind of an anecdote more than something I can say clearly or support with other data.
Okay, if there are no more questions, I think we can officially adjourn and thank Eric one more time. If anyone wants to stick around, I imagine Eric would be happy to entertain some more questions. I actually have a question for Don and Henrietta, if you don't mind sticking around. But officially, let's thank Eric and